would be pi delta omega minus what? And then omega plus what? You're correct, okay? This is the Fourier transform of that. But if I multiply by that window function Wt, and Wt as is given in the example 2.6, Wt is just a rect function T over T naught. Okay, I think that's correct. Okay, let me check again. Example 9.26. Okay, that's correct. T naught, okay? So if you were to plot this thing, when t equals to half T naught, I guess, when t is equal to half T naught, is 1, and then it's minus T naught over 2. So this is how this function looks like, Wt. What is that? Where's the 2 pi? This is the rect function.
Plus 2 pi times delta.
This is 2 pi. This is 2. And then I have that.
And then you multiply by 2 pi when you do
The 2 pi. Should I get it correct? Yeah, I have 2 pi in my notes. Okay, so must be 2 pi. Okay, thank you for pointing that out. So this is the rect function. So you're going to take this rect function to the Fourier space. And we know how to figure out what the Fourier space of this is. And this is just a, when you take a rect function to the Fourier space, what do you get? A sinc function, right? And then you can do a table lookup, or if you don't like table lookup, then you can just do it yourself. Derive from first principle. Okay? And now, when you're asked to find the Fourier transform of Ft multiplied by Wt, this is a measurement. Okay, this is a measurement that you have done in the lab. You just turn on your instrument and turn it off, and you pick up the signal. Okay? And then in the Fourier space, it will be f of omega convolving with w of omega. Okay? And you know how to convolve these two signals, I suppose. So it will be a signal that looks like a sinc function. Okay, a sinc function. If you plot the amplitude of the sinc function, it will look something like this. Okay, this is w of omega convolving with, let me not put a circle, some textbook has a circle, some don't, with a function that are sums of impulses. There is one at omega equals to 4. There's one at omega equals to 8. There's one at omega equals to minus 4. There's one at omega equals to 8. Okay, and they have different heights. Okay, this 2 has a height of 4 pi multiplied by 4 pi. The other one has height of 2 pi. Okay, these impulses at different heights. And then you just convolve these two signals. If the signals are narrowband enough, if you pick the T naught to be wide enough, then this can be very narrow. When you convolve with the two signals, you will get maybe a signal here. Actually, they're all positive definite. And then you will get something here. And then something of a lower height. Okay, the detail can be worked out by yourself.
So it's a canonic convolution.
What is that?
So it's a canonic convolution.
Yeah, we convolve that with that, you get that, right? It's quite easy to convolve with an impulse function. You just replicate the function at the location of the impulse function. Okay? Okay, maybe I have time for one more example. Are there any questions on how to do this example? I won't go through the detail with you. I won't go through the detail of telling you where the zero crossings are. You can figure that out. Yes, Mark?
Wasn't the problem asking you to find the bandwidth of the signal or something?
What is that?
Wasn't it asking you to find the bandwidth of that signal or something?
Yeah, you can find the bandwidth of this signal. Then if you have this signal, then you find that the bandwidth is quite large, right? If you take the total bandwidth, this is called a bandwidth, depending on what you define it. That is the bandwidth. Half power bandwidth or 90% bandwidth, that bandwidth will be given by that number over there. So what it says is that the bandwidth is significantly increased due to this tail end. Okay, originally the bandwidth is only up to here. But then if you convolve with that rect function in the Fourier space, you actually increase the bandwidth. Okay, why does it increase the bandwidth? Can anybody give a physical reason as to why the measurement increases the bandwidth? I have this signal I measure it. G has a larger bandwidth than the original signal. What is the reason for that? What is that? Yes, I convolve that with that. Of course, I get a larger bandwidth. It is a pictorial way to say it. Yes?
Things that are smaller or like less wide in the time domain or wider in the frequency.
Yeah, you can also invoke that uncertainty principle. If something is wide in the frequency domain, it has to be narrow in the time domain, and vice versa. That's called the uncertainty time bandwidth product. Okay, so bandwidth in one Fourier space times the time width in the other space. That is always a finite quantity. One other way to look at this signal is that you truncate it abruptly. Okay, when you truncate the signal abruptly, what must you do? This was a nice, smooth signal. It has only two Fourier harmonics. You take this signal and truncate it and get it to go to zero abruptly. And when signal goes to zero abruptly, what do you need? Yes, you are what? Liu Chun-zhang? You know the answer? No? Okay. So we always know that if you have the signal that has an abrupt jump, okay, then the Fourier transform to something that is quite broad, a sink. It has a long tail. A long tail meaning that it has to have a lot of high frequency components to constitute back to this signal. Okay. A sharp discontinuity always needs a lot of Fourier harmonics. Okay. So if you truncate the signal abruptly, you need a lot of Fourier harmonics. So you need added bandwidth. You need additional bandwidth in addition to this omega equals to 8 point. And that added bandwidth comes from the rect function. The rect function has this additional bandwidth because it needs a lot of high Fourier harmonics to constitute it, to construct it. Is this clear? This is the kind of intuitive reasoning that you should develop. Okay? Let me see if I have time for one more example. Maybe I'll do example 9.29. Okay? Maybe that is quick enough. Okay. The other examples you have to read by yourself. Let's see if we can do that last example. What is that? Let me see. Let me try to finish example 9.29. You're given a unit step function, and you're asked to find its Fourier transform. Okay, a unit step function is also called a power signal because at any given time you have finite power. Okay, but its Fourier transform is actually infinite in power, energy, and you can write a unit step function in terms of a sine function. The sine function is a function that has this property that for t larger than 1, it has a sign of 1, and for t less than 1, it has a sign of minus 1. It just picks up the sign of t. Okay, this is a sine function. And you can write this unit step function as this. If you add half to this, if you multiply it by half, and then just add half to this function, you have half of this function, adding to half of that function, you get a unit step function. Okay, that's what this thing says. And then you're asked to find the Fourier transform of the unit step function. Okay? So the half part is easy. You just Fourier transform to delta omega. Okay, the half part, Fourier transform to half delta omega. What about the sine function, the sine function? What does the Fourier transform to? Okay, that is what this exercise does. And you can think of that if I have a sine function, if I were to differentiate it, okay, if I were to differentiate the sine function, okay, what do I get when I differentiate the sine function? I get, remember when I differentiate a unit step function, we get something. This resembles so much like a unit step function. Okay, so when I differentiate the sine function, what do I get? A delta function, very good. Okay, a delta function. Okay, if I take half of that thing and differentiate it, I get a delta function. And I know how to Fourier transform a delta function. We already derived the Fourier transform identity, so I know that the derivative of the sine function must Fourier transform to, what does the Fourier transform to? What does the Fourier transform to? 2, right? Or 3? Or ducks?
No, 2.
Okay, so if this thing Fourier transform to that, okay, sin of t must Fourier transform to 2 over j omega. Okay, because a Fourier transform and its derivative is just related by j omega. So the Fourier transform of a sin function, not a sin function, a sine function, is just 2 over j omega. Okay? I think this is the gist of this example 9.29. Are there any questions? I cannot go over all the examples in this section, but you can read them yourself. Okay, next time we will see how the sampling theorem comes about, how you can convert an analog signal to a digital signal. And that is the power of a cell phone. Okay?